Welcome everybody to this sixth webinar in our Train Talks at 12 series on wheel rail friction management. Today we will be looking in more detail about energy consumption and how friction management can help reduce energy consumption and improve vehicle fuel efficiency. I'm Jackie Butterfield. I'm the lead applications engineer for LB Foster in Europe. And today, joining us as our guest presenter is Mathew Holland, who is our global product lead for onboard technologies. So I'll be keeping an eye on the chat and any questions that you might have while Matt is speaking. If you have not managed to watch any of our previous webinars, don't worry, they are all recorded and the links are available on our website, and you will get the website link after this event in an email. So on today's agenda, we will start, as we always do with these webinars, just as a quick recap in why we need to control friction in the wheel rail interface. And then Matt will take over the presenting role and talk about energy consumption requirements for rail vehicles, friction management solutions, the consumables that we would use, and some case studies. And then I'll pop back just to talk to you about our final two webinars that are coming up in the next couple of months. So, as always, why do we need to control friction? So again, without friction, there would be no movement of vehicles, but we need to control the friction at the wheel rail interface, because uncontrolled friction may lead to damage, mechanisms and issues such as excessive wheel and rail wear, rolling contact fatigue, curving squeal and flange noise, corrugation damage. Low adhesion, low friction levels can lead to wheel flats, signals passed at danger and braking issues, and ultimately to vehicle collisions. Higher fuel and energy consumption, high lateral forces, and also there are safety issues with high friction related to wheel climb derailment. So I will now hand over to Matt, who will take you through the main body of our webinar today.
Thanks, Jackie. Hello, everyone. As she says, my name is Matt Holland, and I'm here to present this webinar on railway friction energy consumption and its relationship with friction management. So we're going to jump straight in to a scale-looking equation known as the Davis equation. So this equation considers the factors that influence the energy consumption of a rail vehicle. It can be broken down into three segments. Rolling and curving friction considers the influences between the vehicle and the track form. For curving, this is specifically the interrelationship between creepage, bogie angle of attack, and the curving forces. As a vehicle enters a curve, the bogie develops an angle of attack, and because of this, a lateral creepage occurs at the leading wheel set. This lateral creepage generates curving forces. The magnitude of these forces has a direct impact on the magnitude of the energy consumed as the vehicle negotiates the curve, because energy is required to overcome these forces. The second influential component is wind resistance, such as headwinds, tailwinds, and crosswinds. Here, energy is required to overcome the disruptive influence of these winds. A simple example would be to consider what happens if you were to ride directly into wind on a bicycle. In order to maintain the same velocity, additional pedal power is needed to overcome the forces acting against you and the bike. And finally, the last component is grade resistance. Moving an appreciable mass up a slope requires additional energy to overcome the effects of gravity. When we consider the influence of friction management, it can be expected that the terms related to rolling and curving friction can be positively affected. In terms of how friction management implementation can improve rolling and curving resistance, we must consider both the application point of the material and the track feature that the vehicle is negotiating. As a callback to prior webinars, we apply lubricants to the gauge face and the wheel flange with the intention of reducing friction values to between 0.1 and 0.2. For the top of rail, we are aiming to achieve a controlled intermediate friction value of between 0.3 and 0.4. So referencing the table on the slide shown, for medium to short curves where the vehicle is considered to be in constant flange contact, a lubrication regime at the gauge face and wheel flange can have a positive impact. These impacts vary depending on the specific application point. Applying product directly to gauge face via a trackside system can provide superior levels of resistance reduction. However, when modifying the wheel-rail contact at the railhead, it is significantly more impactful, as it does address the root cause, which is reducing longitudinal and lateral creepage. With top of rail friction management applied, the bogie will experience improved steering, which reduces the angle of attack and subsequently the lateral forces imparted on the infrastructure. This means that energy is spent doing more productive work, which is propelling the vehicle forwards. This top of rail phenomena is also present for tangent and shallow curves. For tangent sections, this is translated into a reduction in rolling resistance via reductions in microslip. We would typically not apply lubricant to the gauge face in tangent or shallow curve locations where flange contact is intermittent. In this instance, onboard sticks are found to be highly effective because they build up a lubricant film layer on the wheel flange that can effectively replenish at the non-contact intervals. It can be concluded that the most impactful approach to reducing rolling and curving resistance, therefore, is to actually implement friction management solutions that address both gauge face and top of rail contact. When we consider the grade conditions that influence potential energy savings from friction management, we can break these down into three simplified cases, being ascending, level track, and descending. In both the ascending and level track scenarios, energy is predominantly expended by the vehicle overcoming rolling resistance and curving resistance, as previously discussed. For the ascending scenario, we must additionally consider the grade resistance. In a descending scenario, typically the vehicle will be either coasting or under a form of braking. Generally, that would be dynamic braking. In this scenario, there is no opportunity to save energy from the influence of friction management because there is no throttle-based activity. Therefore, no energy is being expended. However, modern electric vehicles can harvest energy through regenerative braking in a descending grade. In this instance, the energy is used for either heating, lighting, or it can be stored in batteries. Therefore, when we appraise the potential for energy savings on a route conditioned with friction management, the percentage of the route that is considered ascending grade, in addition to the percentage of the route that is considered curving, are the critical considerations. We'll now look at the friction management solutions that can be deployed to assist in train energy reduction. Specifically, we will focus on the onboard application of CalTrack from a sprayed system called a KOB, which stands for CalTrack onboard. This system offers a cost-effective means of conditioning the whole network. So the schematic on the screen shows the constituent parts of the KOB. In practice, these components comprise three common sub-assemblies. A dispensing and controls cabinet, a human and vehicle interface, and the dispensing nozzles themselves. We'll cover these sub-assemblies in more detail on the next slides. It should be noted, however, that the system does require power and air from the vehicle to function. So here is an example of a dispensing cabinet that we recently designed for a transit operator. Items 2, 3, and 6 are common, and they are the pneumatic and product feeds. So they interface with the two spray nozzles via railway-approved hoses. Items 1 and 5 are vehicle inputs. So there's the air position 1, and 5 is our power and signals. In that case, we can also receive discrete vehicle signals. The size and the shape of the cabinet can be customized to suit the available space envelope of the vehicle, but generally these key elements listed are incorporated into all cabinets. The most impactful variable is reservoir size. This is calculated in combination with achieving the operator's desired maintenance intervals and the projected consumption based on a calculated application strategy. Systems do have an allowance for bulk filling to ensure that the most frequent maintenance activity is a quick and easy process. The filling system automatically suspends when the high level sensor in the product reservoir is triggered. So it's a hands-free activity, and you always ensure that you get maximum product fill. If we look at a typical cross-section of the system, we can see the main elements within the tank. There is a small form factor geared pump, which is in consist with a stepper drive motor. This is in turn attached to a manifold that contains temperature and pressure sensors, which feed back to the central controller. In this example, the controller and associated relays are affixed to a backing plate and found within this volume. That's item 5. However, these components can quite easily be housed in a separate enclosure and sited elsewhere on the vehicle, should space be a particular constraint. The dispensing nozzles have been specifically developed to work with Keltrack. So if we refer to this exploded diagram, it consists of an internal nozzle body, which houses a pneumatically operated control pin and an internal volume. Control pin is normally closed. The nozzle body is shrouded by 2 enclosures to protect it from debris ingress. The lower of these enclosures contains a threaded interface to allow mounting to custom-made bracketry. It is generally affixed to the bogie frame. The metallic bodies are manufactured from aluminium to save on weight. The nozzle is considered an external mix type, whereby the fluid stream is atomized at the outlet via compressed air to form a conical shape. It is then propelled towards and deposited upon the railhead. A wind skirt is used to protect the atomized spray cone from any adverse turbulent effects at high vehicle velocities to ensure good transfer efficiency of product. The hose mounting interface contains quick fit connections for the 2 pneumatic feeds, and a union joint is used for the product line. This allows for quick changeouts of the complete assembly should any maintenance activity be required. This ensures that the system can rejoin revenue service without any loss of operation. Here's an image just to show the nozzle in context with the wheel and rail. Generally, the tip of the nozzle will be positioned between 50 and 75 millimeters above the railhead. The other side of the wind skirt is offset sufficiently from the railhead to allow for any dynamic movements of the bogie frame, such as those associated with vertical suspension movements. This just ensures that we avoid fouling the rail. Here's a typical example of the human vehicle interface. So we have a HMI, which is a human machine interface, which allows the operator to interrogate the health of the system, make modifications to the application parameters, or to perform diagnostic tests. Generally, we will have a DC-DC converter to modulate the native vehicle power down to 24 volts, which is what we use to drive the PLC and motors. Finally, signal exchange between the vehicle and the KOB are facilitated via voltage-free optocouplers, so that ensures that we don't have any direct link to the vehicle for safety reasons. This also means, this is a means of isolating us from wider circuits. Here's just a quick example of the sort of information that we can contain on the HMI. So it's fully customizable to suit the needs of the operator and the sort of information that they're interested in observing, and all our software is written in-house. So we can see here, the lower left-hand side is the diagnostic screens that allows operators to ensure that the output volumes are consistent with what's expected, and we're getting products flowing from each nozzle. We'll now briefly just cover the consumable used in the KOB system, which is Keltrack, specifically a form called Keltrack AP. So as per the bullet points on screen, it is Keltrack's a water-based friction modifier, the type that we historically have used on trackside systems. However, the formulation for KOB has been optimized for sprayed applications. It is an engineered composite of inorganic solids, polymers, and friction-modifying additives, which provides excellent protection at the wheel-rail interface. Importantly, it does not contain any oils, which we know can have an adverse impact if not properly controlled. When applied, the product dries under the passage of wheels to form a thin layer. This creates ideal conditions for the intermediate and positive friction at the contact. Interestingly, this layer remains residual on the railhead for several axle passages, so this ensures benefits can be experienced by trailing vehicles that do not have a carrier installed, which is particularly important for systems that run on closed loops. Here are just a list of some of the benefits that we can expect from CalTrack. Of course, today we're talking about the last bullet point, which is energy reductions. However, it's also worth noting that the fundamentals that influence energy savings also have many other highly valuable benefits. All these claimed benefits are supported by prior fieldwork and case study. The formulation is classed as having a low environmental impact and low risk for health concerns. These environmental credentials were a critical component of the assessment recently completed in conjunction with SBB and an independent third party considering its use in Switzerland, where the product has been granted approval on a trial basis until the end of 2026. So in the final part of this webinar, we'll look at some case studies where friction management has been used effectively to reduce energy consumption. Firstly, we'll look at a test conducted to characterize the potential savings on rolling resistance using a coast down investigation. This test was conducted at BNSF, who are a Class 1 freight operator in North America. A locomotive was outfitted with an onboard spraying system to dispense CalTrack. The vehicle was taken up to a target speed and allowed to coast down freely on tangent track. The distance that the vehicle travels while coasting from target speed indicates the amount of rolling resistance present. A longer distance travelled equates to less resistance. This study was first completed without CalTrack to generate an average baseline distance and then compared to values from an applied study. This figure can then, in turn, be converted to a fuel savings figure. The figure of around 50 litres per million tonne miles was observed. This unit allows us to normalise for tonnage and distance travelled, and it's obviously it's the checker point there, the star on the furthest left point of the graph. Subsequent studies were conducted in North America that sought to characterise fuel consumption versus curve density. We were able to study these impacts on a range of routes to build up a clear picture of the relationship. Curve density is the percentage of the route considered to be curved. The data spread is shown to align very well with theory. A greater curve density equates to more sections of the track where the vehicle is having to overcome creepage and lateral loading, and therefore there's more potential for energy savings when friction management is deployed. Several additional studies have been subsequently conducted, some focusing purely on top of rail, while others combine both top of rail and gauge face. The energy saving numbers generated at QCM and UPRR, so they're both, again, heavy haul freight roads in North America, were generated from CalTrack when it was dispensed from a car, so a trailing freight car. What we learn here is it's not always possible to locate that car at the head of the consist. Therefore, more latterly, we have opted to install systems on the locomotive to ensure that all trailing cars receive benefit. I'd just now quite like to briefly cover a recent case study observing the effective impact of KOV, in China on some HXD1 freight locomotives. So this is probably the most recent study that we've done. And it's presented 2 years ago in Rio. So the Baoshan Rail Group is a railway subsidiary of Shenhua Energy Company Limited, and it's responsible for 4 railways: the Baoshan, Shenzhou, Ganquan, and Tahan. This has a total operational track length of 872 kilometres. The Shenzhou Railway is a 270 kilometre west to east Class 1 heavy haul double track electric railway used for coal transportation. Typically, daily traffic is around 200 loaded coal trains eastbound and 200 empty trains westbound. This equates to an annual tonnage in excess of 500 million gross tonnes. The locomotive stock is AC powered, and the locomotives are followed by 108 open-top gondola cars. The Kirby system that were designed for Shenhua was bespoke to suit these vehicles. The system can collect information from the locomotive, such as speed, brake usage, and tangent/curve location, which allows the system to intelligently regulate product application. The system is fully autonomous. An overview and layout of the key components is shown. The locomotive consists of two identical single units coupled together and identified as the A unit and the B unit. The KRB systems are similarly arranged in one unit A and the second B. Each KRB has a 250-litre product reservoir and two dispensing nozzles. They are operated by a common controller, and remote condition information is transmitted via antenna to a web server to allow detailed analysis of system behaviour. The PLC and antenna are only found in the system on the A unit. The systems are programmed to dispense product from the trailing units only. Additional controls logic was also applied. So application rates can be varied based on the track condition. For example, is it in the tangent, is it a sharp curve or a shallow curve? The application rate is also regulated by the speed, so we achieve a specific target at all times. So the dispensings of the order of millilitres per rail per kilometre. And the system is also disabled during full service air braking. For the study, in total, 6 locomotives were outfitted. This is just a pictorial representation of the differences between the A and B systems. So as we can see, they're very much similar aside from the antenna. So as I touched on, the KOB systems operated using a last locomotive in consist logic, which means the product will only be applied if the equipped system is the last locomotive in the grouping. So the background to that is we don't really want to be applying product ahead of tractive axles because they will basically increase the rate at which we consume fill wear. So we're reducing the maximum benefit of the system. Of the available data, 2 units had the greatest sample size. It's 7040 and 7038, as we can see on these graphs. Regarding 7040, a total of 108 data points were recorded for the control and 32 data points for the applied condition. This unit operates eastbound along the line in a loaded condition. A comparison of the data showed a reduction in energy of 4.4%. Similarly, for unit 7038, 54 data points were used for control and 39 for applied. This unit operates westbound in an unloaded state. To allow a comparison to 7040, the energy consumption values were normalized per metric ton of cargo. This comparison of the data showed a reduction in energy of 5.2%. The data considered points taken across all 4 seasons. It is known that temperature, humidity, and precipitation alter contact conditions. Therefore, an additional refinement of results looked to eradicate the effects of comparing data points taken from different seasons. Comparisons were made over a smaller period, so in the case of 7040, that was between July and September, and for 7038, that was between September and January. This resulted in improved energy savings of 6.9 and 6.8% respectively. The Kirby hardware proved to be an excellent technology for optimum application of FM material, and the energy reductions achieved were impressive. As a result, the customer decided to implement this technology across 3 of their railways. So, to conclude, friction management can have a positive influence on reducing rolling and curving friction, which is one of the key drivers in vehicle energy consumption. Top of rail friction management is the most influential when targeting energy reduction. However, gauge face lubrication can also have positive impacts by reductions in curving resistance. The ideal approach should consider a combination of both top of rail and gauge face application. The biggest opportunity for energy savings is when the vehicle is traversing ascending grade or negotiating curved sections. Applying product from an onboard setting can provide greater value when compared to equivalent system coverages from trackside systems. There are also operational safety benefits from implementing an onboard delivery system. CalTrack is field proven to be an effective means of reducing energy. Typically, this has been in the range of 3 to 7%. So we've probably got, that's the last one I've got. I can hand back over to Jackie now, but I guess in the interim, if there's any questions, we'd be happy to take those as well.
Yep, if you have any questions, please just pop them in the chat for Matt. So while you're putting any questions in, I will just tell you about our train talks at 12. So the next event will be on Thursday, the 6th of March. So we're moving from our normal Wednesday. And this is because there's actually an event in the UK organised by the Rail Safety and Standards Board that clashes with our usual Wednesday slot. So we're moving to a Thursday instead. And at that webinar, I will be talking about derailment and how friction management can mitigate and prevent some of the causes of rail vehicle derailment. And then our final webinar in the series will be on Wednesday, the 9th of April. And here we'll talk about validation and trials and best practice. So really, how is the best way of getting the most out of your friction management regime? And how do you know that it's working? So that is all that we have. I will switch to the chat and see if we have any questions. No questions so far? So all that remains is to thank you for attending. This webinar will be up on the website in the next hour or so for people to view back. And I look forward to speaking to you next month. Goodbye.